Hello, my name is Ben Kluczewski, and today I'll be going over Lab 2, Charged Tapes, continuation of Lab 1. Alright, up first we're going to go over what will be in this presentation. First up with the introduction, which will be a description of the lab and the fundamentals. Next up we'll have observations, data, and calculations. Then we'll have Glowscript and the model produced by the code I wrote. After that, finally, we'll have final questions and a few final thoughts on the matter. Alright, first up, the goal of this experiment is to use clear Scotch tape to observe, analyze, and estimate the amount of transfer of charge between the two tapes. This time, instead of representing them as point charges, they'll be represented as line charges. And the charge tape will be introduced to the opposite charge tape to produce repulsion. Our objective is to determine how much charge is present in a piece of charge tape. Now we'll use a few principles in this experiment. We'll use Newton's laws, in addition to electric field and force equations, to calculate relationships and results of interacting charged objects. And our objective in this experiment is to, again, more accurately represent the charge tapes, this time as line charges. Here's a larger explanation on the principles we'll be going over. Coulomb's law, which was primarily used last time, we use this specifically to represent those point charges. We're using electric field formula. Gravitational force will be used to calculate the force offsetting the electric field produced, creating a suspension in midair. We'll also be using Newton's law, specifically the second law. Again, the tape will be in equilibrium, suspension in midair. Results and assumptions and approximations. There were several approximations made in this. First of all, we ignored air resistance on moving objects. Second, we need to take into the fact that neutral matter can be attracted to charged objects due to polarization. Not integral to this, but it should be taken into account. This time, instead of treating it as a point charge, we treated the tapes as line charges, which should hopefully result in a more accurate prediction of charge. And we also assumed that charge across the tape was relatively evenly or perfectly evenly distributed, though in reality that wouldn't be the case. The setup is largely the same this time, with the length, the mass all being the same. We can calculate the magnitude of gravitational force as roughly 0.00196 newtons, which means the magnitude of electric force acting on the tape must be the same, as the tape will be suspended in midair. These are the calculations of the previous lab, where we used point charge estimation, and we found the charge of each tape to be roughly 1.31 times 10 to the -8th coulombs. We'll see later if this charge remains consistent across this next experiment. In this lab, we calculated it using line charges. Again, we find with Newton's law the force of gravity, again, the same as last lab, 0.00196 newtons approximately. Coulomb's law was used in the last lab, but this time we'll use the principle of superposition, which uses integration over a series of segments of line. In this case, we use 10 segments to produce a charge more evenly distributed in the form of line. This time we found the charge to be approximately 2.757 times 10 to the -8th coulombs. Here's the Glowscript model that was produced by the code I wrote. Tape A and B are shown as segmented line charges on the right, with tape A being represented by an array of blue balls and B by the array of red balls. The balls themselves are represented by the segments of the integration. The yellow arrow pointing downwards is indicative of the gravitational force acting on tape B while it remains suspended in air. The smaller assortment of green arrows are representative of the individual electric forces calculated via the line charge method, again the integration. The large white arrow pointing upwards indicates the sum of all the individual charges, again the green arrows, and is equal to the magnitude of the force of gravity, simply acting in the positive y-axis. The two larger arrows cancel each other out, leaving tape B suspended. Now the what-ifs and whys. So what if you'd model each of your tapes as a single point charge like in the previous lab? Compare the values you got. Again, we found the value in the first lab to be approximately 1.31 times 10 to the negative 8th. This time it was 2.76 times 10 to the negative 8, an increase of roughly twofold. And as for why these estimates differ, it's because we use the principle of superposition in this model rather than a single point charge method, which uses a integration formula and produces a line which represents more accurately the even distribution of charge across the tapes. As such, the line method of evaluation is more likely to be closer to the real value. Alright, thank you.